Welcome friends to the lecture series of antenna and wave propagation. Today's topic is we continuing same the previous lecture one we are carrying about the fundamental parameters of antennas. Okay. So, the content of today's lecture is, first of all we understand the relationship between effective height of antenna and effective aperture of antenna, then directivity and resolution, then signal to noise ratio SNR, which is very important for communication system designing. Then we move on antenna temperature, and last we solve few numerical problems related to this. So, before starting, let me summarize till now what we have to learn this in this course, antenna and wave propagation. So, we started with the basic definition of antenna, its working, how it will radiate in free space, and then we move on the fundamental parameters of antenna like radiation pattern, directivity, gain, radiation intensity, etc. So, one more thing, we understand the basic mechanism in order to have radiation. So, related to this we further move on to the next topic, that is relationship between effective height and antenna aperture. As I earlier stated that effective height of antenna is nothing but ratio of induced voltage to the incident electric field. Okay. So, in this slide you can say that effective height is nothing but relation of induced voltage to incident electric field. So, the dimension of this quantity is nothing but volt per meter, voltage का volt divided by volt per meter. So, volt to volt cancel. So, dimension is simply meter. So, this is the effective height. Now, in order to derive the relationship between effective height and aperture and area AE. So, let us begin with, suppose I have an antenna having radiation resistance RR and it is matched to its load. Okay. I have an antenna having radiation resistance RR and it is perfectly matched to the load. Okay. The power delivered to the load is maximum and it is given by this relation, P is equal to power delivered is nothing but V square time divided by 4 RR. Here RR is the radiation resistance and V is voltage. Now, coming to this relation, we can simplify, V is nothing but effective height multiplied by electric field. So, using this relation in this equation, we further simplify our equation in this form. Okay. Moving to this, now let us assume that capital S is our Poynting vector. Remember the concept of Poynting vector, half real E cross H. So, same scenario, and one more thing, this relation is also valid for Poynting vector. Power is nothing but the vector into area. So, this relation we are recalling over here. Okay. So, using this relation we have written over here. One more thing, we further simplify this into this scenario or this term. Here Z naught is intrinsic impedance. What is intrinsic impedance? It is free space impedance and its value is nothing but 377 ohm. Its value Z naught, its value is 377 ohm or 120 pi. Okay. So, from where we can derive this? Remember this concept, the intrinsic impedance or free space impedance is nothing but ratio of E by H, or in some terminology we represented it neta. So, same here we are using abbreviation Z naught, neta or Z naught is nothing but free space impedance, it vary person to person and book to book. Okay. So, E, it is a ratio of electric field to the magnetic field. From here we can say that H is nothing but E by Z naught, and using this relation in this equation we further simplify in form of E square divided by Z naught free space impedance and multiplication of effective aperture AE. So, here is equation number 2. Now, the both power is equal. So, we just compare this two equation number 1 with equation number 2. Okay. So, here you can see that it is free space impedance or intrinsic impedance. So, one we compare this, electric field to electric field cancel out, and the remaining terminology is this, and this is known as the relation of effective height to the effective aperture of antenna, or in alternate we can derive relation in terms of AE also. Okay. So, what is AE now? So, it is a square root. So, you need to square this HE square, okay, Z naught divide by 4 this value R R. Okay. So, this is our relation. What we have done? We square both side and then simply cross multiply it. So, using this we will get this relation of effective aperture in terms of HE. In these two relation, remember one thing is common, it is either is directly proportional to radiation resistance or inversely proportional to radiation resistance. So, radiation resistance play an important role over here, as well as free space impedance, which is act as a constant 377 value. Okay. So, this is the relation between effective height and antenna aperture. Okay. Why we are discussing this? Because it is important, because at the end of the for perfect at end of the perfect radiation pattern or perfect radiation to happen, the radiation resistance must be matched to the load. Okay. So, what we are doing, Z A is equal to Z Z. Remember the concept of antenna basic Thevenin equivalent circuit. So, this way we have to match it, and using this we can decide the height factor of antenna, okay, for different applications. Okay. Moving to the next topic, directivity and resolution. Okay. So, in last lecture we discussed about what is directivity. Directivity is nothing but it is a ratio of antenna or antenna electric field to average over isotropic direction all 360 degree. Okay. Remember that concept, directivity is greater than realized gain quantity. Okay. So, this is we discussing about now resolution. Directivity we already discussed it. So, I am moving directly to resolution part. Resolution is nothing but resolution can be defined for an antenna, it is equal to 1 by 2 of half power beam width or bandwidth between first null. Resolution is nothing but 1 by 2 of first null beam width. We can also relate in this HPBW, because FNBW by 2 is nothing but half power beam width. Okay. This relation is mentioned over here. So, what it represent? For example, suppose I have an antenna which first null beam width is nothing but 37 degree, then can you tell me what is the resolution of that antenna? Yes, obviously, just put this value 37 by 2. So, half of this value is nothing but your resolution factor. Okay. This way we have to define it. Now, moving to this, also the beam area can also be defined in terms of this relation. Beam area is nothing but multiplication of longitude factor to the latitude factor. You can just revise this concept for radiation pattern when we discuss longitude, latitude, azimuthal, elevation angle. Okay. So, it is a product of half power points at theta plane to the half power points at phi plane. Theta plane is nothing but elevation plane and phi plane is nothing but azimuthal plane, or we can say longitude, this one is latitude, theta represent for latitude and phi is represent for longitude. So, it is a product of these two value, okay, because sometime in numerical it is given directly the value of theta h p and phi h p. So, using this relation we can directly calculate what is our beam area. Okay. Now, let capital N is a number of transmitter, because we are discussing the resolution in terms of practical scenario, because in open environment there are number of transmitter and number of receiver. So, we have to visualize this also. So, let assume there is capital N number of transmitter distributed uniformly over a given area. Okay. uniformly distributed over given area, okay, which antenna can resolve. So, it is given by capital N is nothing but the solid angle, beam solid angle, the maximum value of a sphere for solid angle is 4 pi divided by the beam area. Okay. But if you recall this, this is nothing but directivity. We discuss in directivity 3-4 formula. So, this is directivity from beam area, we have derived this or we discussed this. So, from here what we can see this directivity is nothing but number of transmitter. What it represent? It represent that if we apply or put numbers of antenna for a given area, then its directivity is very high, and that is we are using the concept of directional pattern. So, for an application which require directional or high quality of bandwidth, high quality of service, we need to employ number of antenna, transmitter antenna to that particular area, so that its directivity will improve, because directivity is directly proportional to gain. Okay. Remember this, directivity is nothing but this, or we can say that gain is nothing but, this is not, gain is nothing but epsilon into d. Epsilon is efficiency of antenna. Oh, okay. But efficiency is not 100%, because losses associated with the material, the conduction losses and the dielectric losses. So, gain or directivity is directly proportional to each other. So, higher the gain, higher the directivity, higher the directivity, higher is the gain. Okay. So, this is the relation between directivity and resolution. Okay. Next, signal to noise ratio. So, you have heard about this term SNR, signal to noise ratio, and very oftenly used in communication systems. Okay. So, as we know that any signal which is not intended to a particular receiver side is treated as unwanted signal, and this unwanted signal is nothing but noise, because we do not want that signal, but it is coming from somewhere, some places, because there are numbers of scatterer or number of transmitter utilized in free space scenario. Okay. It is very easy to verify this, just go to the rooftop of your house and see how many transmitter or BTS are installed over here. So, it is not necessarily that one BTS is dedicated to you, because it is assigned in such a way cell to cell you move, and BTS is going to take your care by signal strength. Okay. So, in a communication system, any undesired signal is treated as or known as noise, and the ratio of signal power to the noise power is known as signal to noise ratio. I am repeating again, the ratio of signal strength or signal power to the noise power is signal to noise ratio. Okay. So, it is better to describe in terms of decibel dB. So, simple 10 log 10 P signal power to the noise power, same we have mentioned over here, or you can write let's S by N. Okay. Signal strength or signal power or power of noise. So, this is the ratio in terms of decibel, we described 10 log 10. Okay. Okay. Now, one more thing, there is one more factor, that is noise factor, capital F. Okay. What is this? It is a ratio of SNR of input signal to the SNR of output signal. See, it is a ratio of SNR of input to the SNR of output signal. Let us derive this. Noise factor F is nothing but SNR of input to the SNR of output. What is SNR of input? SNR is nothing but S of divided by N. So, what we write? S input oblique N input divide by S output oblique N output. Simplify just in terms of input. So, S input oblique divide by N input, same SNR output, S output divide by N output, or further we can rewrite the cross multiplication S input into noise factor of output divided by S output into noise factor of input side. So, this is the relation of noise factor for a given system. It is a ratio of input SNR to the output SNR. Okay. So, recall this again, any unwanted signal is nothing but noise to a particular receiver, because if there is number of receiver 1, 2, 3 and I am transmitting a signal which is only intended to receiver 1, then some portion of that signal can be intercepted by receiver number 2 and maybe it is possible for receiver number 3 also. So, for receiver number 1 it is intended signal. Okay. So, this is known as message signal for receiver 1, but for receiver 2 and 3 it is act as a noise signal, because they do not want it, because transmitter is only sent to receiver 1, not to receiver 2 or 3. Okay. So, that treated as a noise signal. Okay. So, it is a ratio of signal strength to the noise strength or power of noise. Okay. So, here is the details about signal to noise ratio, because the basic detail, the ERFC and other things you were heard or discussed in later on, or basically it is only this part we are dealing with what is the basic definition. Okay. Next, another important topic is antenna temperature. Okay. What is antenna temperature? Now, every object with a physical temperature above absolute 0, that is at 0 Kelvin, which is nothing but minus 273 degrees Celsius, will radiate energy. Every object with a physical temperature, if there is a physical temperature, will radiate, but it is a poor form of radiator as discussed. Some may act as a good transmitter, but it is not a good radiator. But some, and another example, everyone using laptop. So, the socket, the switch from where the source is coming to your laptop and battery is charges, it also acts as a form of antenna, but it is a poor. How? Because it is a 2 wire, one wire is carrying current input and another carrying output. So, out of phase, due to out of phase field generation, the effective radiation is cancelled out and thus it acts as a poor radiator. So, this way we can see that every object with some physical temperature can radiate. The amount of energy radiated is usually represented by its equivalent brightness temperature. Okay. This is here we are discussing brightness temperature, because we have lots of light sources available to us. Okay. The sun, it also scatter, but it is in terms of brightness factor, the star, the moon, etc. So, it is all nothing but black body radiation, you heard about this term. Okay. So, it is known as brightness temperature and it can be defined as by this relation y theta phi, because we are destined to particular theta angle and phi angle, the direction factor. Okay. So, T theta phi is nothing but efficiency theta phi times T m. What is T m? T m is nothing but molecular temperature, Kelvin. Okay. What is T b? Brightness temperature. What is epsilon? It is emissivity, which is dimensionless, and what is this? We can further relate this into the 1 minus gamma square, which is nothing but reflection coefficient. Okay. Reflection coefficient of surface for the polarization of wave. Reflection coefficient, how we define it? Z input minus Z naught. Remember this formula? Z input minus Z naught upon Z input plus Z naught. What is Z input? Input impedance. Okay. And what is Z naught? The characteristic impedance of that particular wire or conductor. Okay. So, this way we can define this formula. Okay. So, this is T b. Now, what is actual T a, which is antenna temperature? Okay. We discuss about by this formula, but later on first discuss, since the value of this emissivity are varying from 0 to 1 only. It is greater than or equal to 0 and also greater than or equal to 1. So, it vary between 0 to 1. Okay. The maximum value of brightness temperature can achieve is equal to its molecular temperature. So, depending upon different substrate or different physical quantity, the temperature vary. Okay. So, the brightness temperature emitted by the different sources, again this brightness temperature is emitted by different sources, okay, and this brightness temperature is intercepted by antenna, the receiver antenna, okay, and its at its terminal it is termed as antenna temperature. I am repeating again, this brightness temperature emitted by different source present in the universe is intercepted by antenna and it appear at its terminal known as antenna temperature. So, the brightness factor or brightness temperature we defined earlier, and this is emitted by universe in the molecular or having physical temperature greater than or 0 Kelvin or Kelvin to minus 273 degree Celsius. So, this is emitted by different sources in the universe and it is intercepted by antenna at its terminal and it is termed as antenna temperature. Okay. So, now let us derive its formalization. So, T A is nothing but antenna temperature, and if you closely recall this formula, it is nothing but T B, which is brightness temperature which is emitted by different sources, to gain g theta phi sin theta d theta d phi. What is this? This is nothing but solid angle. Remember this, sin theta d theta d phi, and how it is vary 0 to 2 pi for azimuthal plane and 0 to pi for elevation plane, theta plane. Okay. So, this way divide by this g theta phi sin theta d theta d phi. Okay. So, in terms of beam area or beam solid angle, we can further define this temperature T A is nothing but this relation, beam solid angle or the value of brightness temperature received by this emitted from the source and received by at antenna terminal is calculated by this, and the total available beam area psi A, and this is the generalization in terms of beam area antenna. This is for simplifications. Okay. So, this is the actual formula, because it is related to gain, because if source is emitting something, it is treated like brightness temperature and it is directed toward this. So, gain factor is involved there and it is realized gain. Okay. So, this way where T is antenna temperature and g theta phi is gain pattern of antenna. So, this way antenna temperature is defined, because in the universe there are lots of scatterers which can be treated as interference to our signal, and it can emit light, the wavelength, and this wavelength is intercepted by our antenna at its terminal, and this will also add up or may be subtractive in nature depending upon its orientation, phase, polarization, different things associated with terminology, and this way we can define our antenna temperature. So, this is about antenna temperature. Let us discuss the few problems related to our today's study. So, here we first mentioning our first question, calculate the effective length and directivity of antenna having radiation resistance R r is given how much? 73 ohm, okay, and effective aperture is given lambda square, where lambda is wavelength. Okay. So, we have to find out what effective length and directivity. So, earlier we had defined this relation between effective length or effective height. Okay. It is same scenario, effective length or effective height. H is how much? We have derived this relation, it is R r into effective length, effective height to Z naught or free space impedance. This formula is relation between effective height and effective aperture. Remember this, we earlier we described this formula. Now, what we have given? We have given R r, just put over here, we have given effective aperture, just put over here, but in this question there is no frequency given over here. So, you can calculate just calculate in form of lambda wavelength, no problem, because in antenna the calculation may be considered in form of wavelength lambda, it is perfectly right. Okay. So, just put over here what we have given 73 ohm to 0.13 lambda square divide by 377. Okay. When you simplify this, there is your final answer of effective height. Okay. So, just calculate it, it is up to you, just calculate it, simple calculations. Okay. Now, next part what is this asking? So, first we have calculated, and second part is directivity. Can you recall the relation of directivity with effective height? Remember the formula 4 pi A e upon lambda square. Okay. So, utilize this formula and we can calculate 4 pi A e upon lambda square. Again A e is given in form of lambda square. So, lambda square to lambda square cancel out. So, simply we will get 4 pi into 0.13. So, the typical value we can get from here, just calculate it, okay, and we will get our answer directivity. Directivity is dimensionless. Okay. So, this way we can solve this problem. See, we have this relation between effective height and effective aperture, and we also know that directivity is nothing but 4 pi a upon lambda square. Okay. We have derived, this is the relation of directivity from effective aperture, the third formula. Okay. So, this way we can simplify. Okay. Moving to the next question, what we have given, calculate the effective aperture of antenna having half power beam width angle which is given 30 degree and 35 degree, and assume side lobe level are very low or negligible. So, we have given theta h p and phi h p. This is the only possibility which is given to us, azimuthal and elevation plane. This is the only possibility, theta and phi, because it is associated with a space coordinate system. So, theta phi which is we have given. So, there is one new formalization to this problem is directivity, sorry, we have to calculate one. We have to calculate effective aperture. So, how we can calculate effective aperture? Just using this formula, that is d lambda square upon 4 pi. And how we can calculate directivity? Directivity can be calculated, there is a one more formalization which is approximate value of directivity, which is given as 41257 square degree divided by theta h p and phi h p, which is given to you theta h p and phi h p. So, from this formula, remember this formula. Okay. This is just conversion of stereo solid angle conversion, 1 radian 180 divided by pi. So, square of that is degree square. So, from here we have calculated this solid angle over a sphere is 4 pi times of that value. Okay. Remember this, we discussed this in the measure of radian plane angle and solid angle. Okay. So, this is our formalization, theta h p and phi h p is given to us. So, just put over here, calculate the value of directivity over here, and from here when d is known and lambda, in terms of lambda we will get our effective aperture. So, this way we can solve this type of problem. Okay. So, only you have to recall the fundamental or basic relation whatever we have discussed in this or earlier lecture. So, let us summarize what we have learned today. We learned today the effective height and aperture relationship. Okay. So, next we learn our signal to noise ratio SNR, then we learn about antenna temperature and how brightness temperature play an important role when deriving the TA antenna temperature and its problem between directivity calculation and effective aperture calculation. So, this is it for today's lecture. Thank you.